Let's think about it this way. The fastest thing we have ever launched from Earth is the Voyager 1 spacecraft. Beautiful machine. We launched it in 1977, and right now, it's just barely leaving our solar system. It's moving at about 17 kilometers per second. That sounds fast. 17 kilometers every second. New York to Los Angeles in about 4 minutes. Not bad. But here's the thing. At 17 kilometers per second, to get to Proxima Centauri, you would need about 73,000 years. 73,000 years. Now, 73,000 years ago, human beings were just beginning to paint on cave walls. We hadn't invented writing. We hadn't invented agriculture. We hadn't invented anything. And that's how long it would take our fastest spacecraft to reach just the nearest star. So right away, you see, the problem isn't subtle. The problem is enormous, gigantic. The distances are so vast that even before we start talking about physics, even before relativity enters the picture, we're already in trouble just with the pure arithmetic of it. Now, the obvious response to this is, well, we need to go faster, much faster. We need to build rockets that go not 17 kilometers per second, but maybe 30,000 kilometers per second, 10% of the speed of light. At that speed, you could reach Proxima Centauri in about 42 years. Still a long time, but now we're at least in the realm of a human lifetime. You could imagine someone being born, growing up, spending their whole life on a ship and arriving. So let's ask the question, can we build a rocket that goes 10% of the speed of light? And here is where the real physics starts to bite us. There's a wonderful equation, and I want you to appreciate this equation not just as a formula, but as an expression of a deep truth about nature. It's called the Tsiolkovsky rocket equation, and it was derived by a Russian schoolteacher named Konstantin Tsiolkovsky at the end of the 19th century. Beautiful man. Sat in a log cabin in Kaluga and worked out the mathematics of spaceflight before anyone had even built an airplane. The rocket equation tells you something that seems almost unfair when you first see it. It says the ratio of your initial mass, that's the rocket plus fuel, to your final mass, that's the rocket without fuel, grows exponentially with the speed you want to achieve. Exponentially, not linearly, exponentially. What does that mean in practice? For a chemical rocket where you're burning hydrogen and oxygen, the exhaust velocity, the speed at which gas comes out the back, is about 4 kilometers per second. Now, if you want to go faster than your exhaust velocity, you have to carry an enormous amount of fuel. And the more fuel you carry, the heavier the rocket, and the more fuel you need to accelerate that fuel too. It compounds, it multiplies, it gets out of hand very, very quickly. To accelerate a modest rocket to just 1% of the speed of light using chemical propulsion, you would need a mass ratio, fuel to payload, of something like 10 to the 450. That's a 1 followed by 450 zeros. For comparison, there are only about 10 to the 80 protons in the observable universe. The number of protons in the universe is nothing compared to how much fuel you'd need. The whole observable universe isn't big enough to be your fuel tank. So chemical rockets are out. Completely out. Not almost enough. Not even remotely close. We're not talking about a factor of 2 or 10. We're talking about factors that are literally incomprehensible. All right? So we move to something better. What if, instead of burning chemicals, we use nuclear energy? Fission, or better yet, fusion. Fusion is what the sun does, squeezing hydrogen nuclei together to make helium, releasing enormous amounts of energy. The energy density of fusion fuel is about 10 million times greater than chemical fuel. 10 million times. Now we're getting somewhere. With fusion propulsion, the exhaust velocity could potentially be a few percent of the speed of light. And with that kind of exhaust velocity, the rocket equation becomes somewhat more manageable. You could imagine, in principle, reaching 10% of the speed of light with a fuel-to-payload ratio that's large, but not cosmically insane, maybe a few 100 to 1. But here's the catch. We haven't built a fusion reactor that produces more energy than it takes to run, not even one on Earth sitting still, with all the power of our civilization to help it. The sun does fusion easily because it has the gravitational weight of 1,000,000 Earths to squeeze the hydrogen together. We have to do it with magnetic fields and lasers. And after 60 years of trying, 60 years of brilliant engineers and physicists and billions of dollars, we are just now getting fusion reactors that break even, just barely. And that's a fusion reactor that sits still on the ground. Building one that produces thrust in space is a completely different problem. But let's be generous. Let's say we solve fusion. We build a beautiful fusion drive. We get a ship to 10% of light speed, 42 years to Proxima Centauri. There's still a problem that doesn't go away no matter how good your engine is, the interstellar medium. Now, the space between the stars isn't empty, not truly empty. It's very, very thin, much thinner than any vacuum we can create on Earth, but it contains hydrogen atoms, helium atoms, dust grains, and other particles scattered very sparsely through space. On average, maybe one hydrogen atom per cubic centimeter. That sounds harmless. One atom per cubic centimeter. But here's the thing. When you're moving at 10% the speed of light, 30,000 kilometers per second, those atoms are not slow bumps in the road. They're incoming projectiles. From the ship's point of view, they're hitting you with enormous kinetic energy. Every single hydrogen atom becomes a little cosmic ray particle slamming into the hull. The flux of particles at that speed is significant. You'd need shielding, heavy shielding. And the heavier your shielding, the more fuel you need to accelerate it, and so on. The rocket equation bites you again. And it gets worse. At higher speeds, say 50 or 90% of light speed, even a dust grain, a tiny interstellar dust grain, maybe a micrometer across, carries enough kinetic energy to punch a hole straight through your spacecraft. A small pebble at those speeds would be like a nuclear weapon going off inside your ship. So to go very fast, you need extraordinary shielding. But shielding is heavy, and heavy things require more fuel, and more fuel makes you heavier still. Nature has a very wicked sense of humor. Now I want to get to the deep physics, because everything I've told you so far is, in some sense, an engineering problem. Hard? Yes. Maybe impossibly hard in practice. But in principle, you might imagine clever solutions, better designs, better materials, better engineering. What I want to tell you now is something different, something that isn't an engineering problem, something that's a law. In 1905, a young man working in a patent office in Bern, Switzerland, published a paper that changed forever our understanding of space and time. His name was Albert Einstein, and the paper was on what we now call special relativity. Einstein started with two simple postulates, two things he assumed to be true. First, the laws of physics are the same for everyone moving at constant velocity. It doesn't matter if you're sitting still or moving, as long as you're not accelerating, the laws of physics look identical. Second, the speed of light in a vacuum is the same for everyone, always. No matter how fast you're moving, no matter in which direction, if you measure the speed of light, you get the same number, about 300,000 kilometers per second. Now those sound innocent. They sound almost obvious. But when you take those two simple ideas and you follow them, when you work out the mathematics of what they imply, you get results that seem absolutely crazy. And yet every experiment we've ever done confirms them, every single one. The first result, you cannot accelerate any object with mass to the speed of light, not with any amount of energy. The closer you get to the speed of light, the harder it becomes. Here's why. As an object moves faster, according to special relativity, its inertia increases. It becomes harder to accelerate. The faster it goes, the more energy you have to put in to make it go even slightly faster. And as you approach the speed of light, the energy required approaches infinity. Literally, you'd need infinite energy to reach the speed of light. And since we don't have infinite energy, we don't have infinite anything. The speed of light is an absolute wall. This isn't like a technological barrier. It's not like the sound barrier, where clever engineering got us supersonic aircraft. The sound barrier was a practical challenge. The physics allowed it. The engineering had to catch up. The light barrier is fundamentally different. The physics itself forbids it. The same equations that tell you light speed is impossible also tell you why GPS satellites need relativistic corrections and why particle accelerators work the way they do. This isn't speculation. This is the most tested theory in the history of science. But wait, you might say, and I like this objection, it's a good one, what about time dilation? Because special relativity also tells you something extraordinary. The faster you move, the slower time passes for you relative to someone who is stationary. This is real. This is not science fiction. We measure it with atomic clocks on airplanes. We measure it with muons created in the upper atmosphere that shouldn't live long enough to reach the ground but do because their time runs slow. Time dilation is real. So here's the idea. If you could get a ship to, say, 99.9 99.99% of the speed of light, then from the perspective of the people on the ship, time would be passing incredibly slowly. A journey of 1,000 light years might feel like only a few years to the crew. In principle, you could cross the galaxy in a human lifetime from the crew's perspective. This seems like a loophole, a beautiful loophole. Time dilation saves us, but it doesn't. And here's why, and this is the part I really want you to think about. First, there's still the energy problem. Getting to 99.9999% of the speed of light requires extraordinary energy. The relativistic momentum of a ship going that fast is enormous, much, much larger than Newtonian mechanics would suggest. The energy required to push a ship of even modest size, let's say 1,000 kilograms, which is tiny, less than a car, to 99.9% of light speed is roughly equivalent to the total energy released by detonating 100 million hydrogen bombs. And that's just to get up to speed. You also have to slow down at the other end. Where does that energy come from? The best fuel we can imagine, matter-antimatter annihilation, has an energy density that's theoretically perfect. You put in matter and antimatter in equal amounts, and you get pure energy out. 100% conversion of mass to energy. Nothing could be better. But even with perfect antimatter fuel, you need a mass of antimatter and matter combined that is much larger than the payload. Much, much larger. And we currently produce antimatter in quantities measured in nanograms. Less than nanograms. The amount of antimatter we've ever produced in all the particle accelerators on Earth, if you annihilated all of it at once, wouldn't light a light bulb for a second. To produce enough antimatter for an interstellar mission, you would need to scale up antimatter production by perhaps 20 to 23 orders of magnitude. That's not a factor of 1,000 or 1,000,000. That's a factor of 100 million trillion. And the process of making antimatter requires, at minimum, exactly as much energy as the antimatter will release when annihilated. So you're not gaining anything in terms of energy. You're just converting energy into a storable, portable form. So you need to find some enormous energy source to make the fuel in the first place. Second problem with time dilation. Even if the crew experiences only a few years, the people on Earth experience the full journey time. If you travel to a star 500 light years away at near light speed and come back, you return to an Earth that has aged over 1,000 years. Everyone you knew is dead. Human civilization has moved on or collapsed. This might be philosophically interesting, but it makes communication and coordination across civilizations essentially impossible. Third problem, at very high speeds, the interstellar medium problem I mentioned becomes catastrophic. The cosmic microwave background radiation, the leftover glow from the Big Bang, which is everywhere in the universe, which you cannot avoid, gets blue shifted by your motion into hard X-rays and gamma rays. At sufficiently high fractions of the speed of light, the crew would be bombarded by lethal radiation from the vacuum itself. The universe irradiates you for going too fast. It's like nature is saying, I gave you a speed limit and I gave it teeth. Now, I know what some of you are thinking. What about wormholes? What about warp drives? What about general relativity? Einstein's general theory of relativity, his theory of gravity, published in 1915, does contain solutions to its equations that seem to allow faster-than-light travel. Wormholes, tunnels through space-time connecting two distant points. And more recently, Miguel Alcubierre proposed in 1994 what's called a warp drive metric, where space itself is contracted in front of a ship and expanded behind it, so the ship isn't moving through space so much as being carried by it. These are real mathematical solutions to Einstein's equations. They're not crackpot ideas. They're legitimate physics, but they come with problems that appear to most physicists to be fatal. First, they require something called exotic matter. Not exotic in the sense of unusual or rare. Exotic in the very specific sense of having negative energy density. To hold open a wormhole stable enough to travel through, to make an Alcubierre warp bubble work, you need matter that has negative energy. Negative. Like it doesn't just have very little energy, it pushes the other way. We know this kind of thing can exist in tiny quantum amounts. The Casimir effect gives you negative energy between two very closely spaced metal plates. But the amount of negative energy you'd need for a traversable wormhole or a warp drive is, by current estimates, on the order of the mass energy of Jupiter, or maybe more, and we have no idea how to produce or collect or manipulate exotic matter in any significant quantity. we have no idea if it can even exist in the amounts required. Second problem, there's a thing called the chronology protection conjecture, proposed by Stephen Hawking. The worry is that if you can build a device that allows faster than light travel, you can use it to also go backward in time. You can construct what's called a closed time-like curve, a path through space-time that loops back to where you started, and that opens up causality paradoxes, the grandfather paradox, effect preceding cause. The logical structure of the universe begins to unravel. Hawking believed, and many physicists believe, that quantum effects will always conspire to prevent such things from being stable. The universe, as it were, protects its own causality, but this isn't proven. We don't have a complete theory of quantum gravity that would definitively tell us. Third problem with wormholes. Even if you could construct one and stabilize it, you can't use it to communicate faster than light with the past, because to create a wormhole, you have to get the two mouths of the wormhole to the right places. And to do that, you have to move one of the mouths. And you can't move it faster than light. So you're back to light speed as a constraint, at least for establishing the infrastructure in the first place. There's another beautiful and depressing argument I want to share with you. It's called the Fermi Paradox, and I think it's deeply relevant to our discussion. Enrico Fermi, brilliant physicist, built the first nuclear reactor. One of the sharpest minds of the 20th century was having lunch with some colleagues in 1950, and they were talking about UFOs and extraterrestrial life. And Fermi said simply, "Where is everybody?" The galaxy is about 10 billion years old. It's full of stars. Many of those stars have planets. Many of those planets are billions of years older than Earth. If interstellar travel were achievable, if a civilization could spread from star to star, even at just 1% of the speed of light, they could colonize the entire Milky Way galaxy in about 10 million years. 10 million years sounds long, but the galaxy is 1,000 times older than that. Any civilization that arose even 1 billion years before us and could do interstellar travel should have colonized the whole galaxy long before we appeared. And yet, nothing. Silence. No alien megastructures, no signals, no visitors, no evidence whatsoever of any civilization anywhere in the observable universe, despite the fact that there are 2 trillion galaxies out there, each with hundreds of billions of stars. One possible explanation, and I want to be clear, it's not the only explanation, is that interstellar travel genuinely is as hard as the physics suggests. Maybe it's so hard that no civilization ever manages it. Maybe the great filter isn't behind us, some catastrophe that kills civilizations, but ahead of us, the physics itself. The universe builds these beautiful, diverse solar systems and then wraps each one in an enormous void that nothing can practically cross. Each civilization lives and dies in its own little island, separated by distances no engineering can overcome in any human-relevant timescale. That's a sobering thought, but I don't think we should find it just depressing. I think there's something clarifying about it. Because here's what I believe, and I want to be careful to say I believe this not as a scientist. This is more philosophical. But I believe the value of asking, can we get there, is not primarily to answer yes or no. The value is what you learn in the process of asking. When you work through the physics of interstellar travel, you learn about special relativity. You learn about rocket propulsion. You learn about nuclear physics. You learn about general relativity and the structure of space-time. You learn about the interstellar medium, about cosmic radiation, about the nature of matter and antimatter. You learn about the deep structure of the universe. All of that is remarkable. All of that is enriching. And sometimes along the way, you find something unexpected that changes the picture. Who knows? Maybe there's a physics we haven't discovered yet. Not a violation of what we know. I don't mean that. I mean an extension. The way general relativity extends special relativity. The way quantum mechanics extends classical mechanics. There may be a layer of physics beneath what we currently understand that reveals new possibilities. I can't promise you that. I can't even tell you it's likely. But I can tell you that every time in history that physicists thought they understood the fundamental rules completely, every time something new came along. Usually something strange and beautiful and completely unexpected. In the 1890s, physicists thought they were almost done. They had Newton's mechanics. They had Maxwell's electromagnetism. They had thermodynamics. What could possibly be left? And then came the ultraviolet catastrophe and Planck's constant and Einstein's photoelectric effect and the quantum revolution, everything changed. So I won't tell you that the physics we know today is the last word on what the universe permits. Nobody said that about any previous era of physics, and they were always wrong to imply it. But I will tell you this, the obstacles to interstellar travel as we currently understand physics are not minor. They are not things that will yield to slightly cleverer engineering or slightly bigger budgets. They are fundamental. The energy scales involved are astronomical, literally astronomical. The distances are staggering. The physics of acceleration and mass and time itself conspire against us in every direction we look. And the most interesting thing to me, the most philosophically fascinating thing, is this. The same physics that prevents us from traveling to other stars is the physics that makes stars exist in the first place. The nuclear physics that makes fusion so energetically powerful is the same nuclear physics that powers the sun for billions of years and creates the heavy elements that make rocky planets and make us. The relativity that limits our speed is the same relativity that governs black holes and gravitational waves and the expansion of the universe. You can't separate the physics that creates the beauty from the physics that creates the limits. They're the same equations. They're the same universe. So when someone asks me, does it bother you that interstellar travel seems impossible? I always want to say, no, it fascinates me, because the impossibility itself is a window into the deepest laws of nature. And understanding those laws, really understanding them, not just reciting them, but feeling why they must be true, that is one of the greatest pleasures a human being can have. The universe is very large, and we are very small, and we are stuck, at least for now, at least with the physics we have, in our little corner of it. But we can understand it. We can sit here on this small rock orbiting an ordinary star in an unremarkable galaxy, and we can work out equations that describe what happens at the edge of a black hole and what happened in the first fraction of a second after the Big Bang and why the stars shine. We can figure out with pencil and paper why we can't go to those stars. And in doing that, we've learned something remarkable about what kind of universe we live in. That, to me, is not depressing. That is the most exciting thing I can imagine. Thank you.